Fleming's left and right hand. Okay, so Fleming's left and right hand. I will tell you, Nana, first of all, what is the importance of Fleming's left and right hand? Okay, so the two last important is to find the direction only. Okay, the two last important one is to find the direction. Okay, but what is the difference between that left and right hand rules? Okay, what is the difference between the left and right hand? Here is Fleming's left hand rule. I'll just show you now, no issue for that. Okay, I'm saying generally. Okay, so the Fleming's left hand rule is used for to find the direction of motor. Okay, the Fleming's left hand rule is used to find the direction of motor. Okay, and similarly, Fleming's right hand rule. Okay, so Fleming's right hand rule is used to find the direction in case of generator. Okay, in case of generator. Gen means what is the output of a generator? Either EMF or current. Okay, so the Fleming's right hand rule is used to find direction of EMF or current. Similarly, what is the output of a motor? See, what is the output means here? Suppose when fan is there, what is the function of a fan? It is rotating. And what is the function of an AC? Again, it is rotating. Every output of a motor is rotating. Rotating means either force or torque. These are the outputs of a motor. So, to find the direction of the force or torque, we use Fleming's left hand rule. To find the direction of EMF, we use right hand rule. So now we will see now how to find the direction here. See, first we go for right hand. Right, this is the right hand, right? So I think I'm visible. Right. I think I'm clearly visible, right? So Fleming's right hand rule means here we have to take our these three fingers. Okay, we have to take our these three fingers, thumb finger, forefinger, and middle finger, and we have to keep like this. Okay, all these are in perpendicular to each other. Okay, all these are in perpendicular to each other. So in this way, if I keep, and this thumb finger represents force direction. Okay, force direction, and the middle finger represents, sorry, the forefinger represents magnetic flux. Okay, the forefinger represents magnetic flux, and the middle finger represents direction of the current or EMF. Okay, thumb finger represents magnetic force, and forefinger represents magnetic flux, and middle finger represents direction of the current. Okay, so how we can that means, remember, easily means father, mother, child. Father, mother, child. So father means force, mother means magnetic flux, child means current. So the Fleming's right hand rule is also, left hand is also same concept. Father, mother, child. Father means force, mother means magnetic flux, child means current. Okay, so but that is a difference here. In case of motor, we give the current. That means we give middle finger and forefinger. This is the direction of the force we try to find. But in case of generator, we give the force and magnetic flux, and we will find the direction of current. But in case of one mark questions, they will ask generally. Okay, that's why I'm showing that. Okay, simple. You have to write what is meant by thumb finger, what is meant by index finger, what is meant by middle finger. That's it. So thumb finger represents direction of the motor motion. Index finger represents magnetic flux. Middle finger represents induced EMF or current. That's it. This is sufficient. Okay. Right. So next concept is self-induced EMF and mutually induced EMF. Okay. See, according to Faraday's laws, what we have understood here, so we understood that when, if I am taking a coil, or I will take multiple coils, then we can understand here. Okay. See, generally we represent multiple coils like this. Okay, so when change in flux linking these coils, EMF is induced. Okay, so how the flux is produced here? That starting we have discussed, right? Flux we can produce by using artificial flux. That is, when I am giving voltage, alternating voltage, so due to that alternating flux is produced. So when this alternating flux linking the coil, what happens here? EMF is induced. So this is we call as self-induced EMF. Okay, this is we call as self-induced EMF. Clear? So when a coil is connected to a battery, due to that battery, flux is produced. When this flux linking the coil, EMF is induced. That is we call as self-induced EMF. And similarly, we have mutually induced EMF. Okay, so we see what is meant by mutually induced EMF. That means if we observe nearby the first coil, I am taking a second coil, but I am not connecting any voltage source to the second coil. Okay, I am not connecting any voltage source to the second coil. But what happens here? The flux in the first coil or first circuit passing through the air and linking the second coil also. Okay, the flux of the first coil or first circuit passing through the air and linking the second coil also. Now what happens according to Faraday's law? Again EMF is induced. Okay, so we want the change in flux, whether it is related to the same circuit or another circuit, we don't bother. When there is a change in flux linking the coil, EMF is induced. Now this EMF we call as mutually induced EMF. So this is we call as self-induced EMF. Okay, so what we can understand from this one, Anna? Suppose EMF is produced due to the flux with respect to the same circuit. That is we call as self. But suppose if EMF is produced due to the flux with respect to another circuit. Flux with respect to another circuit. That is we call as mutually induced EMF. Okay, so simple way if I want to tell you, if we are spending your money, that is called as self-spending, or if we are spending others' money, that is called mutual. Okay, so that is the difference between self-induced EMF and mutually induced EMF. Okay, now, right. So I am trying to explain the concept now. Okay, that is the main concept. After that, you can write in your work. See, next one is about the transformer. Okay, so first of all, what is a transformer? See, generally we represent the transformer like this, right? Okay, so here if I am giving the input and here I take the output. Okay, so where I am giving the input, that is we call as primary winding. Where I am taking the output, that is we call as secondary winding. Okay, so what is the function of a transformer? So transformer is a device. Here I am giving an input P. I am getting the same output P. Another point. I am giving here. Okay, I am getting here the same output I am getting. But what is the difference here? Suppose if I am giving here V1 and I1, but here I am getting V2 and I2. Okay, so transformer is a device. It transfers the power from one point to another point. Okay, it transfers the power from one point to another point. That is the main function of a transformer. So, but what is the difference? Okay, what is the difference in transfers here? Transfers are different levels. Transfer the different level. That means in the starting case, if P is equal to, if I am giving 5 into 10, that means 5 voltage and 10 amps, then output side, what it is gives here, 10 voltage and 5 current. Clear? See, overall power value, product of these two is same both sides, but the difference here is change in the levels. Suppose if it is increasing the voltage, automatically decreases the current value. Okay, that is the main function of a transformer. See, which is a transformer, the same. So this is we call as primary winding, this is we call as secondary, and here we are giving input, and here we are taking load. Okay, so this rectangular box we call it is a core. Okay, the rectangular box we call it is a core. We have a two main parts of a transformer. One is a core, and second one is a winding. So these we call as the windings. Okay, this rectangular box we call it is a core. Second one, that is an ideal transformer. Okay. What is the difference between ideal transformer and practical transformer? Okay, ideal transformer, practical transformer difference. So ideal means generally it is not existed. Okay. Ideal means generally it is not existed. So practical means exactly for the practical condition. So first coming to the one point, efficiency. Okay, generally any machine we just verify the performance based upon the efficiency, right? So we take the efficiency. So what is the efficiency in practical cases? So practical cases, definitely what is the efficiency in general? It's less than 100. Right? What is the efficiency formula? Efficiency at a simple how much percentage you got in your intermediate. So how we'll calculate here? How many marks you got divided by the exam total marks, right? So 920 divided by 1000. So your percentage is 920. Suppose if ideal case, how I will say here 1000 divided by 1000. So 100% is efficiency. So 100% means ideal cases. So in ideal case, I will get the 100% efficiency. In practical case, definitely it is less than 100. Okay, right. That is a major difference. So here we are getting 100% efficiency. What is mean by this one, Anna? So there are no losses. See here, if you are getting 920 marks, Anna, how many marks we lost here? 8. But here, if you are getting 1000 marks, means there is no loss of marks. So if there is no loss only, we get 100%. So in ideal cases, there is no loss. But practical cases, some amount of power is lost due to materials, either in transformer core as well as transformer winding. Okay, so that is the ideal case. There is no losses. So if there is no loss, means where we get the loss first of all? In transformer windings. Why? Because transformer winding is made up of some part of the resistance. So due to the resistance, some amount of the power is lost. But here loss is 0. What is mean by that one? There is no winding resistances. That means the windings have 0 resistance. Okay. Similarly, there is no leakage of flux and permeability is high. So these are the main points which will say the transformer is an ideal or practical transformer. Okay. In case of practical transformer, permeability is little bit low, leakage flux is existed, and loss is also existed. Okay. So that are the differences, Nana. And EMF equation of a transformer. See, from the Faraday's second law, we have discussed, right? What is the Faraday's second law here? Second law, E is equal to change in flux. That is N into d phi by dt, right? So the d phi by dt, I am substituting all the values. That's it now. Okay, I am substituting all the values. See, this is a sinusoidal equation we are taking. Alternating waveform in sinusoidal only, right? So in this sinusoidal waveform, I try to substitute d phi and dt values. Okay, d phi and dt values. So what is a d phi means? From 0 to pi. So this change in flux I am taking. Initial value is 0, final value is pi m. So this change in flux I am taking. So this change in flux, in how much time the flux is going from 0 to pi m. The flux is going from 0 to pi m. So the total time period here is t. Okay. The total, see, you can see here now, the total time period is t. The half time period is t by 2. And again it is a quarter time period. So it is t by 4. Okay. T by 4 is the time period. And we know the relationship between time and frequency is T is equal to 1 by F. So here I am writing 1 by 4F. I am substituting those values. Pi m d5 change in flux and pi m. Pi m means maximum to 0. So pi m minus 0 divided by 1 by 4f. So this is a EMF induced in a single turn. That is a average EMF. Okay. The generalized equation here is for average EMF. But what we need generally RMS. So what I am taking here, I am taking form factor to find the RMS value from average. So RMS value is equal 1.11 into average value. So what is this 1.11? Yesterday we have discussed, form factor is equal to RMS value by average value. The RMS form factor of a sinusoidal waveform is 1.11. It is standardized. So if I substitute all the values, so this is the EMF equation. Okay, then this is N. What is N here? This is for one single turn. But a coil consists of more than one turn. So that's why I am represented generalized term for turns is N. Okay, so this is a EMF.